Okay. So, in today's class we shall discuss about implementation of elliptic curve cryptography. So, as we have seen in the previous classes is that elliptic curves and elliptic curve cryptography essentially relies upon point operations like point addition and point doubling operations. So, they are all actually quite computational intensive operations, right. So, therefore, if I want to develop either a software or a hardware, we need to take some more or that there are some interesting developments how you can actually implement it in much more efficiently. Okay. So, today's discussion will be based on this. So, we shall discuss about scalar multiplications and we shall discuss about whether LSB first or MSB first is approach. I mean we will try to compare between these two approaches. Then we will discuss about Montgomery technique of scalar multiplication and discuss about fast scalar multiplications without pre computations. Like before this there were some people, I mean there were some implementations which were actually based on pre computed values of, suppose I want to compute lambda p. So, there were like some pre computed values were already stored and then they were combined to compute the value of lambda p. This one approach could be like, if I want to compute lambda p, then you take the binary encoding of lambda and you keep certain values of say maybe 2 lambda, 3 or 4 lambda, 8 lambda stored and then you combine them in order to obtain the value of lambda p. Okay. So, they are actually like scalar multiplications using pre computed tables, right, but there may be applications, I mean you may not be interested in spending so much amount of memory, and they were quite nice paper. I mean there is a nice paper by Lopez and they have to show how you can actually do fast scalar multiplication without pre computation. So, we will study that and we will study about Lopez and they have projective transformation to reduce the number of inversions or finite field inversions which are necessary, discuss about little bit about mixed coordinates, not go much into details and rather concentrate upon some parallelization techniques which can actually accelerate the scalar multiplication operation. Okay. So, let us go step by step. So, therefore, this is the how the broad diagram of elliptic curve hierarchy looks like. So, you can see that the basic elliptic curve operation is based upon point multiplication, called it Kp, that is k is a scalar and p is a base point, and the other is that it is based upon group operations which are point addition and point doubling. Okay. And that is again underlyingly based upon the finite field operations like addition, subtraction, inversion and so on. Okay. So, now you see that that means that there are various levels of how this elliptic curve cryptographic operation works. So, therefore, if I want to obtain accelerators, then I will try to parallelize these architectures, right. So, I will try to parallelize the point multiplication, I will try to parallelize the group operations, I will try to parallelize this underlying arithmetic operations. So, therefore, for what is important is to understand where are the scopes of these parallelizations or how you can actually obtain these accelerations, right. So, first let us concentrate upon how to do this scalar multiplication operation. So, there is a point p and we are interested in computing k multiplied by p. Okay. So, k is my scalar which can actually be written as a binary, can be encoded in a binary format, call it k0, k1 until km minus 1. So, km is actually the first time when 1 is encountered, previous to that everything is 0. You understand this? So, therefore, if I want to encode 7, it will be 1 1 1. If I want to encode 5, that is if k is 5, then it is 1 0 1. Previous to that it is all zeros. Okay. So, therefore, very simple way is what is known as the double and add algorithm. So, what we do is that we take this p and store in a temporary register, call it q, and for I equal to m minus 2 to m minus 0, that is this is the first one, right. So, therefore, we start from m minus 2 and go till 0, and whenever we see that we always do a doubling operation, and whenever there is a 1, then we do a q equal to q plus p, that is the point addition operation. So, this in this case you are actually parsing the scalar from MSB to the LSB. This is the least significant bit and this is the most significant bit. So, we are going from MSB to LSB. So, therefore, this algorithm is called MSB first. Okay. So, in this case what is the total number of computations necessary? You see that it requires, if there are roughly if you just say that it is m, that is the length is m, it requires roughly m point doublings because you are always doing a doubling operation. Okay. It is actually from m minus 2 to 0, so it is m minus 1, but approximately I have written it just throwing away the constant term. Okay. that is roughly it requires proportionate to m point doublings. Okay. What about the number of additions required? So, generally if you assume a random k, the k will have half number of ones and half number of zeros if k is just thought to be a, if I consider the average complexity of this algorithm. So, in that case there will be m minus 1 by 2 point additions which are necessary. Okay. So, therefore, I need to do so many number of point additions, that is half number of point additions, right. That is the rough cost of this algorithm. So, therefore, you can consider an example. If I want to compute 7 into p, I will encode 7 as 1 1 1. So, you note that this is the first time when you have got a 1. So, when you are encoding from MSB, then this is the first one that you are actually considering. Okay. If it is a 1, then you have to do not only a 2 into p, but also add that with the corresponding p, that is you have to do the doubling as well as you have to do an addition operation. And next one is again a 1. So, again that means again you are doing a doubling and adding with p, that is 2 into 2 p, you see that 2 p plus p is 3 p into 2 is 6 p plus p is 7 p. So, you see that 2 iterations are required, the first one is double and then add, that is the principle. Okay. So, first you are doing a doubling and then you are doing an addition or accumulation operation. So, similarly if you want to compute 6 p, it is 1 into 1 into 0. So, in this case you have to do, because of this 1 you have to do into 2 into p plus p, but since this is 0 you have to do only a doubling operation, you do not need to do the addition operation, right. So, in this case you see it is 3 p into 2 which is 6 p, right. So, that is the MSB first approach of obtaining the scalar product, scalar term, scalar multiplication. Similar to this, you can actually do an LSB first algorithm also, that is where you go from k0 and go to the MSB. So, in this case again you see that km is 1 and these are the corresponding terms, corresponding binary values. So, now I want to compute again q equal to k into p. Now, for this what we do is that we actually, instead of having one register, we actually choose two registers, call one of them as q and the other one as r. So, what we do is that we initialize q to 0 and r to the value p. Okay. Now, from I equal to 0 to m minus 1, if ki is 1, then we add onto this register q, that is q is equal to q plus r, and in the other register we are actually doing a doubling operation. Okay. So, here you see that as opposed to the previous algorithm we were doing a doubling and then you were doing an addition operation. So, that means there are two steps which you cannot actually parallelize, they are sequential steps, right. But in this case, because you are doing these operations on two different registers and actually you are actually giving more space, you are actually saving time. So, you can actually parallelize these two operations and you can do the accumulation and the doubling in two different registers simultaneously, right. You can do this q equal to q plus r, and in the other register you can do this r equal to 2 into r operation, right, and this you can repeat for all these values. So, therefore, the accumulation and doubling can be stored in separate register. On an average there are m by 2 point additions and m by 2 point doublings which are necessary. Why so? Now, because you are doing the addition and doubling in two separate registers, right. So, therefore, always there is a cost of m by 2. So, therefore, you see that you are, whenever there is an addition required. So, if you assume that half, if this k has got half 1 terms, then half of the times you will have, that is m by 2 times you need an addition operation, that is m by 2 addition, and when you do not need an addition you need a doubling operation, right. So, therefore, the total time is m by 2 point additions plus m by 2 point doubling operations. Now, why it is not m point doubling operations? Because the addition generally will take more time than the doubling operation. So, even if you parallelize, you can assume that the addition will actually take more time. So, you have to wait, since there are two parallel steps, you have to wait for the longest time, right. So, that is m by 2 point additions, and then you have to do the rest of m by 2 point doubling operations, right. So, therefore, you see that there is some advantage, because you can actually parallelize this algorithm through this. Okay. So, therefore, this is the LSB first approach of doing it. So, therefore, now you see that this also can be seen, the same 7 p and 6 p example. So, here it is 1 1 1, q is equal to 0 and r is equal to p. Now, you see that in 3 time steps you can actually do this q plus r, and in parallel you can do this r equal to 2 into r operation, Okay. So, because this is a 1, now you are doing LSB first. So, you are first starting with this 1, this is a 1. So, you are doing an addition, you are doing a doubling. Next time you are again getting a 1, so you are again doing an addition, again doing a doubling operation here. Okay. Next time you are again seeing a 1, you are doing an addition, you are doing a doubling operation here. So, where is the result? The register is in, the result is in Q. Similarly, when you are doing 1 1 0, the first thing is 0. So, therefore, 0 means you are not doing the addition operation. So, Q is unaltered, unaffected. Okay. R is doubled, so R becomes 2 into R, right. Next you get a 1, so therefore, you add 0 with 2p, that is you add the current value of Q and the current value of R, and it becomes 2p, you double R, it becomes 4p. Okay. Next time you add 2p with 4p because it is a 1 and you double, but this is inconsequential because the final result is stored here 6p, right. So, therefore, you see that you can still do the computation 7p and 6p, what in this case you are actually parsing from the right and going to the left, right. So, you see that there are small implications whether you are doing from the left to the right or from the right to the left, which you can use to your advantage depending upon the platform where you are implementing your constraints. Okay. So, therefore, one example here shows that if I want to compute 31p and this is an MSB first approach and this is the LSB first approach, you see that there is a significant reduction in terms of the time steps that are required to do this operation, but the cost that you pay is 2 registers, that is the cost which you are paying. Okay. So, therefore, when we can say that there is more scope of parallelism when you are doing or taking an LSB first approach, right. So, now let us actually, so this is a small point about the scalar multiplication. So, now let us go into the implementations of the elliptic curve, point addition and the point doubling operations. So, this is a recapitulation of the equations that we got in the first class. So, this is the addition of p and q when p and q are not the same. So, this is the equation of adding x1 y1 and x2 y2, and if the points p and q are same, then this is the corresponding doubling point. Similarly, the corresponding y coordinates are shown here. Okay. So, now the question is how do we do this operation. So, here you see that point addition, and another point which is to be noted here, that is if p is equal to x1 comma y1, then minus p is shown as x1 comma x1 plus y1. So, how do you get this minus p? Is you take this curve, you take any point x1 comma y1 and draw a vertical line through this x1 comma y1, right. So, wherever it intersects the elliptic curve, that is the negative of p. Okay. So, you can take this and you can solve this, take a vertical point and say call it y equal, it is a vertical point and vertical line, and that you have to basically simultaneously solve with these equations, and then you can easily show that the corresponding minus point is minus p is equal to x1 comma x1 plus y1. So, I am not going into the derivation, which you can do yourself. Okay. You can take it as an exercise. So, now I want to add these 2 points r, p and q, and store the result in the register r. So, you note that point addition and doubling each requires 1 inversion and 2 multiplication operations. So, if you observe your addition and doubling here, you see that you need to do this 1 by x1 plus x2. So, that means that is one inversion operation, and that you need to multiply with y1 plus y2 in this case. If I just consider the addition operation, in this case you need to multiply with also with x1 plus x3, that is one more multiplication. So, note that multiplications with constants and multiplication and squarings are neglected, because that I believe that you can, that we believe that we can also do it without multipliers. Okay. So, the other thing is if you see that corresponding doubling equation, there also you need to operate this 1 by x1. So, that is one inversion is necessary. Similarly, the same 1 by x1 can be used here also. The other thing is the multiplication with is x3. Okay. So, that is the corresponding 3, that is you require, you also require to multiply this with this y1. So, that is another multiplication. Okay. So, that means you need 2 multiplications and 1 inversion for both point addition and for both point doubling operations. So, we neglect the costs of squaring and addition, and we also neglect the costs of multiplying with constants. Okay. Like here you have multiplied with b, that is neglected. Okay. So, if b is already a pre-known value, a fixed value for the curve, then you can actually develop an architecture which is devoid of multiplication. Okay. Now, the first thing which was interesting behind what Montgomery noticed is that the x coordinate of 2p does not depend on the y coordinate of p. So, if you note that this p equal to q point, I mean when you are doing the doubling operation, then the x coordinate of this output actually does not depend upon the y coordinate, right. So, this was the important observation, that is, you see that the x coordinate of 2p, you see that does not depend upon the corresponding y coordinate, that is, it does not depend upon y1, it is only a function of x1, right. So, based upon this, Montgomery developed, and this was a very important observation, developed a faster method to perform the scalar multiplication. Okay. So, this is actually based upon an invariant property where you say that there are 2 points p2 and p1 and I want to compute k into p. Okay. So, I choose I generate p2 and p1 at each step or at each iteration such that the difference of p2 and p1 is always maintained to be p. Okay. So, I want to compute this kp. So, I first of all encode this in this fashion and I set p1 as big P and this p, and I set p2 as 2p. Okay. And so, you see that p2 minus p1 is what? Is p, and right. So, therefore, what we do is when we vary from I from L minus 2 to 0. So, what is this? This is the MSB first approach. Then if ki is equal to 1, then what you are doing is that you are in P1 you are adding, that is, you are doing P1 plus P2, and in P2 you are doubling, that is, you are doing 2 into P2. But if this ki is 0, then you are actually adding in the P2 register, but while you are doubling in the P1 register. So, you see that whether ki is 1 or whether ki is 0, P2 minus P1 is always invariant. So, you see that P2 minus P1 here is 2 P2 minus P1 plus P2, which is what? Which is P2 minus P1. Similarly, here P2 minus P1 is also P2 plus P1 minus 2 P1, which is again P2 minus P1. So, therefore, P2 minus P1 is actually an invariant for this algorithm. You see that? Right. So, now you are actually doing this addition and doubling in this fashion, and therefore, the idea is that P1 actually finally stores the value of k into P. Okay. So, what are the implications of this algorithm, that how essentially, or what is the relation, I mean what is the efficiency factor, I mean how to implement these operations efficiently. Okay. So, first of all, let us see that indeed it computes what we want, that is the correctness of the algorithm. So, I want to compute 7p. So, therefore, first of all I choose p1 as p and p2 as 2p as we have seen previously, and the steps are, because first we start with this one. Okay. So, therefore, you see that this is 1. So, in p1 what are you doing? You are adding p with 2p, you are getting 3p. What about this p2? P2 you are doubling. Next time you are again getting a 1. So, again in p1 you are adding 3p plus 4p is 7p, and p2 you are doubling, that is inconsequential in this case. In this case it is 1 1 0. So, therefore, in 1 again you are doing 3p and 4p like previously, but next time it is 0. So, you are actually adding in p2. So, therefore, p2 is 3p plus 4p, which is 7p, whereas p1, while p1 is double of p1, so that is 6p. So, again you are returning p1 as the result. So, you see that the correctness of the algorithm is still maintained, right. So, therefore, indeed p1 stores the value of k multiplied by p. Now, what is the, I mean how, rather why essentially is this efficient? That is an important question, right. So, rather why essentially do we do in this fashion? So, therefore, that brings us to this point topic of fast multiplication and elliptic curves without pre-computation, that is, I am not having any pre-computed values and still I am accelerating the computation of lambda p, okay, or k into p. So, for that there are certain results which are important, which I will try to discuss here. That is, suppose, so for that, first of all let us observe the corresponding sums here. Okay. So, the sums of, you know, that x3 is equal to, so I am just writing down the results. So, I am adding x1 comma y1, and if I add x2 comma y2, the corresponding sum is stored as y1 plus y2 divided by x1 plus x2 whole square plus y1 plus y2 divided by x1 plus x2 plus x1 plus x2 plus a right, that is the sum, I mean that is the corresponding sum x axis x coordinate, and the corresponding y coordinate is as shown here as y 1 plus y 2 divided by x 1 plus x 2 into x 1 plus x 3 plus x 3 plus y 1. Okay. So, for at this point let us just concentrate on this term, that is the x coordinate of the result. Okay. So, I want to add this point x 1 and this point x 2 y 2. So, note at this point let us make a kind of restriction also, is that let us only be concerned about elliptic curves which are on points in characteristic 2, that is the elements are chosen from GF 2 to the power of m for any m, for some m. Okay. So, now if I want to obtain the corresponding sum of this x 1 and y 1, or the x 1 y 1 and x 2 y 2, then I can actually simplify this and I can write it as x 1 plus x 2 whole square, and the numerator will be as y 1 square plus y 2 square. Why? Because 2 y 1 y 2 is in 0 right here. So, then you have got here x 1 plus x 2 into y 1 plus y 2. So, that becomes here x 1 y 1 plus x 1 y 2 plus x 2 y 1 plus y 1 y 2, right, plus x 1 plus x 2 whole square, right, other x 1 plus x 2 whole cube. So, it is x 1 cube plus x 2 cube plus x 1 square x 2 plus x 2 square x 1, right, x 2 square x 1, is it correct, x 1 cube plus, we are multiplying this with this, right. So, x 1 cube plus x 2 cube plus x 1 square x 2 plus x 2 square x 1 plus a multiplied with x 1 square plus a multiplied with x 2 square, right. And you note that x 1 y 1 is a point on the elliptic curve. Okay. So, you choose, you know that if this is your equation, then you know that since x 1 comma y 1 and x 2 comma y 2 are points on the elliptic curve, you know that y 1 square plus x 1 y 1 is equal to x 1 cube plus a x 1 square plus b. Similarly, your y 2 square plus x 2 y 2 is equal to x 2 cube plus a x 2 square plus b, right. So, that means if you observe now this term, then your numerator becomes, you can actually combine and you see that you have got like x 1 y 2 plus x 2 y 1, that is this term and this term, okay, plus you can actually write y 1 square plus x 1 y 1 plus x 1 cube plus a x 1 square plus b plus, okay, I am adding a b there, and y 2 cube y 2 square plus x 2 y 2, okay, plus x 2 cube plus a x 2 square plus b. Okay. So, if you do this, then you know that, okay, there are some more terms so there. What is that? X 1 square x 2 plus x 2 square x 1. So, this full thing is there in the numerator, right. Is it so? So, that means this term and this term will go to 0, because they are points on the curve, and being in characteristic 2 field, these two terms goes to 0. So, you have got x 1 plus x 2 whole square in the denominator, and in the numerator you have got x 1 y 2 plus x 2 y 1 plus x 1 square x 2 plus x 2 square x 1. is it correct? Right. So, that is your corresponding sum of x 1 y 1 and x 2 comma y 2, right. So, that is the first result here, which says that your if you take x 1 comma y 1 and if you take x 2 comma y 2 and these are points on the elliptic curve, then x coordinate of p 1 plus p 2 x 3 can be computed as x 1 y 2 plus x 2 y 1 plus x 1 square x 2 plus x 2 square x 1 divided by x 1 plus x 2 whole square. Okay. So, therefore, you remember that the field has got a characteristic 2 and that p 1 and p 2 are points on the curve. So, these are the two things that we have used in this result. Okay. So, therefore, you know that from this that if in this Montgomery's algorithm that we know that p was maintained to be equal to p 2 minus p 1, that was an invariant for the Montgomery's algorithm, right. So, therefore, p 2 was essentially a point like x 2 and y 2 and what was p 1? P 1 was equal to x 1 comma x 1 plus y 1, I mean minus of p 1 is equal to x 1 comma x 1 plus y 1, right. So, therefore, the sum of these two of x 2 y 2 and x 1 comma x 1 plus y 1 is nothing but x comma y, right. So, this is the sum of these 2 points, right. Okay. So, therefore, we know that from here your x, okay, if you say that this x is equal to, I mean you know that this x, you can actually write this x as x 1 plus x 2 whole square into x 1 y 2 plus x 2. So, you can actually use this y coordinate as x 1 plus y 1 plus x 1 x 2 square plus x 2 x 1 square, right. Basically, I am adding up these two things and using the previous result, right. So, similarly, you can add up these terms. Okay. So, and if you want the sum of p 1 and p 2, say call it p 1 plus p 2 and call it as x 3 comma y 3, then your x 3 was what we have previously got. So, I am again writing that x 1 plus x 2 whole square is x 1 y 2 plus x 2 y 1 plus x 1 square x 2 plus x 2 square x 1, this was what x 3. So, you can add these two equations where you will get like x plus x 3 is equal to x 1 plus x 2 whole square, and in the numerator you will see that x 1 y 2, x 2 y 1, x 1 square x 2 and x 2 square x 1, all of them will cancel. So, what you will be remaining with is only x 1 x 2, right. So, therefore, you can actually write x 3 as you can rearrange these terms and you can express x 3 as x plus x 1 plus x 2 whole square into x 1 x 2, right. So, now you see that if you want to do this operation, then how many you need to multiply this, right. So, therefore, the other way of writing this in an equivalent fashion is like x plus x 1 plus x 2 whole square x 1 square plus x 2 divided by x 1 plus x 2. So, this is simple. You see that if I can take x 1 plus x 2 whole square, then x 1 square will stay, x 2 will be multiplied with x 1 plus x 2. So, x 2 square will be there and the other term will be x 1 into x 2, right. So, you see this sorry, there is a small thing, this is x 1, right. So, if in this case this x 1 square and this x 1 square will get cancelled, right. Now, what is the advantage of doing this in this fashion? So, how many inversions do you need to do? You need to do one inversion because you need to compute 1 by x 1 plus x 2, and how many multiplications you need to do? you need to multiply with only x 1. You need to, I want to compute the x 1. So, I basically do a 1 by x 1 plus x 2, that is one inversion. I multiply it with x 1, right. That is how many multiplications? One multiplication, and then I need to do a squaring. So, how many multiplications I did? One multiplication, but here I had to multiply with x 2, I had to multiply with x 1. So, I needed two multiplication operation, right. So, you see that it is quite interesting, the same thing, but if you just rewrite and expand little bit, you see that you are basically saving the number of multiplication operations that you need to do. Okay. And so, therefore, that is your result 2, that is if your p is equal to p 2 minus p 1, okay, then the x coordinate of p 1 plus p 2 x 3 can be computed in terms of the x coordinate as this. So, you see that here whenever you are computing this x 3, that is when you are computing p 1 plus p 2, you are not actually bothered about the y coordinate, you see that, right. That means you can do the operation entirely devoid of y coordinate. So, previously we had already noticed, Montgomery noticed that the doubling was actually devoid of the y coordinate, but then here it was also used, I mean the thing which is used here is that if you maintain this invariant, that is if p is equal to p 2 minus p 1, then the sum of p 1 plus p 2 is also made devoid of the y coordinate. That means you are not actually operating on two coordinates, you are actually operating on only the x coordinates. So, that means you need not care about the y coordinate if you are maintaining this, right, and that actually gives you an amount of efficiency, right. Then you also need to obtain the y coordinate finally, right. So, for that this result is used, that is if p is equal to x comma y and your p 1 is x 1 comma y 1 and p 2 is x 2 comma y 2 be elliptic points, and assume that p 2 minus p 1 is again equal to p and x is not 0, then the y coordinate of p 1 can be expressed in terms of p and the x coordinates of p 1 and p 2 as follows. Okay. So, here you are actually writing this in a different way, that is you are writing this as, you know that your invariant is p equal to p 2 minus p 1, right. So, that is your invariant here. So, therefore, this you can actually rewrite as p 1 being equal to p plus p 2, right. You can always write them in this fashion. That means p points were x comma y and p 2 was x 2 comma y 2 and your p 1 is x 1 comma y 1, right. So, therefore, your x so therefore, you can actually add this. Okay. So, I think I wrote something wrong here, p plus p 1, right, p plus p 1 is p 2, that is p 2 is x 2 comma y 2 and p 1 is x 1 comma y 1, right. So, that means you can use the previous result here to write or express x 2. So, your x 2 is actually equal to x 1 plus x whole square and you have got x 1 y plus x y 1 plus x 1 x square plus x 1 square in the numerator. Okay. So, that means this you can write as, so this is your x 2. So, therefore, if I want to obtain the value of x y 1, if I target this x y 1, then I can express x y 1 as x 2 into x 1 plus x 2 or rather x 1 plus x whole square plus x 1 y plus x 1 x square plus x 1 square, right. That is equal to x 2 multiplied by x 1 square plus x square plus x 1 y plus x 1 x square plus x 1 square. So, now you can actually take out from here, you can take a common of x 1 and you can write it as x 1 x 2 plus x 1 x plus x square plus y, okay, plus x into x 2. So, that is nothing but here x square into x 2 has been written in this fashion. So, x square into x 2 is this term, okay, and in the other part there is x 1. So, therefore, you see that here you have an x 1. So, it is x 1 square into x 2 which has been written in this fashion. Then you have got an x 1 multiplied with y which has been written in this, and then you have got an x 1 square x. So, that is your this term x 1 square x, and then you have got an x square x 1. So, that is x square x 1 is this term. Okay. So, these are actually written in two factors like this. The reason is like if you write x 1 and then now if I add say x 1 x 2 plus x 1 x plus x square and add x 2 plus x square plus y. So, basically I am adding here an x 2 plus x square here, okay, and then in the other term I am also writing x 2 plus x 2 x 1 plus x 1 plus. So, that is another term which you are adding here. Okay. So, do you see this, that this is what this is a new term. So, it is x 1 x 2. So, x 1 x 2 gets cancelled over here. Okay. What is the other term that is added is x square x 1. So, that is x square x 1, okay, and so you see that this is the extra term that is being added over here, right. Is it okay? So, that you can write as, if you take x 1 plus x common. So, you see that here x square and x square will get cancelled out, okay, and okay, there is a plus y term here. Okay. So, there is a additional plus y term here. So, if you see that this one is x 1 into x 2 plus x 1 into x plus x 2 plus y. Okay. What is this term here? X 2 plus x 2 x 1 plus x 1 plus y, that is the same term basically, right. So, therefore, you can take this as common and you can write this as x 1 plus x into x 2 plus x square plus y plus x into y. Okay. So, therefore, now you can actually obtain y 1 from here. You can just take and divide this by x, you should get y 1 value. Okay. That is what is written over here, that is y 1 is equal to x 1 plus x multiplied with x 1 plus x into x 2 plus x square plus y divided by x plus x y by x. So, that is y. Okay. So, that means that you are always doing whenever in this Montgomery's algorithm you are only bothered about the x coordinates and you are doing it. Finally, at the end when you need the y coordinate of the output also, you can apply this equation to get the y coordinate, right. So, therefore, if you write all these things in the form of an algorithm, then this is the way how you can do so. So, you see that here we start with x 1 equal to x, that is the x coordinate of the point, and what does this indicate? X 2 equal to x square plus b by x square. What does this indicate? This indicates it is 2p, right, and I am only bothered about the x coordinate, I am not bothered about the y coordinate. So, x 2 is equal to x square plus b by x square is only the x coordinate of twice p, right. You remember the original Montgomery, this is the Montgomery algorithm, right. So, therefore, we had p 1 storing p and p 2 storing twice p, right, and in this operation I am only bothered about the x coordinates. So, therefore, here we only stored the corresponding x coordinates, it is x and this is x square plus b by x square. Now, what we are doing is that we are calculating a value of t equal to x 1 by x 1 plus x 2, okay. And then if this value is 1, then we are doing an addition operation here. The addition operation is defined only by doing x plus t square plus t. So, that is only the x coordinate of the corresponding sum of p 1 and p 2 of p 1 and p 2, okay, or rather x 1 and x 2, and here you are storing the doubling thing, and when this value is 0, here you are doing the doubling in x 1 and you are doing the addition operation in x 2, okay. And do you understand why it is x plus t squared plus t? That is from the result 2, right, that is from the result 2 where you are doing this operation. So, this is your t. So, this is t square plus t. So, you are doing that t square plus t only to do the addition operation. Okay. So, finally, you need to obtain the y coordinate. So, therefore, you can obtain the y coordinate by doing this operation. Okay. So, what is the advantage here? You can see, I mean, what is the number of inversions, multiplications, addition and squaring required here is shown here, which you can work out. Okay. So, therefore, it is like if you want to do the inversion, you see that you are always doing an inversion operation. So, it is 1 by x 1 plus x 2 means that is a cost of one inversion always, and whatever you do, you are always doing an inversion either here or you are doing an inversion here. So, that means it is a two inversions which are necessary, right. So, there is one here and there is either this one or this one. So, that is two inversions multiplied by the number of times you are doing this or running this loop, okay, plus 1 because you are doing another additional inversion operation here. Similarly, you can also count the number of multiplication operations here, additions and squarings. Okay. So, you see that here still you have got a large number of times you have to do this inversion operation. Okay. So, that means that, and you know, I mean, that inversion is actually a very costly step in finite field operations, right. So, therefore, there was, in order to reduce this number of inversions, these affine coordinate systems were actually converted into something which is called as projective coordinates. Okay. So, that is basically a 3-dimensional space which is being borrowed to reduce the number of inversions which are necessary. So, for example, when n is greater than or equal to 128, each inversion is actually like equivalent to 7 multipliers in hardware design. Okay. That means there is a lot of cost, and therefore, there is an importance of reducing the number of inversions. So, therefore, there was one projective coordinates which is called as a Lopez. They have projective coordinates where x, y and z are the 3 projective systems, and x, the affine system small x is actually equal to x by z, and the small y is written as y by z square. Okay. So, that is being written as this x comma y comma z equivalence class. So, the motivation is to now replace these inversions by the multiplication operations and then perform one inversion at the end to obtain back the affine coordinates. So, what is done in projective coordinates is that all the operations of addition and doubling are done devoid of any inverses. They are done at the cost of increased number of addition operations, okay, and increased number of multiplication operations. And finally, there is a necessity of converting the output from the projective coordinates back to the affine coordinates. There we need to do one more inversion step. So, for example, here if you remember that in doubling, this was the corresponding equations in Montgomery system. So, these are the values which are being shown here, that this you need to do 2 inverses, 1 general field multiplication, 4 addition and squarings. If you convert this into the projective coordinates by the previous transformations that we have seen, okay, then you will see that you actually need to do 0 inverses. There are no inverses necessary, but you need to do increased number of multiplication and addition and squaring operations. Okay. So, therefore, depending upon your m is to I ratio, that is the number of multipliers in your inverses, this may become handy, okay, and may help to make your implementations more efficient. Okay. So, therefore, if you convert this entire system into projective coordinates, this is how the Montgomery's algorithm looks like. Okay. So, here you see that here you have set your x as x1 as small x, z1 as 1, and x2 is x to the power of 4 plus b, and z2 is x square. Okay. So, x to the power of 4 plus b is, so you see that x2 and z2 are storing what? Are storing the double point, and here it is storing the single point. Now, you are doing, if ki is equal to 1, you are doing in projective coordinates the addition operations in x1 y1, okay, and you are doing the doubling in the x2 z2. Okay. So, you see that you are not actually working on the y2 point. Why? Because your Montgomery's algorithm, Montgomery's technique does not need me to work on the y coordinate, it just needs only the x coordinate. Okay. And when your ki is 0, then also you need to do the addition here and the doubling in the x1 z1 register. And finally, when you have got the result, then you need to convert this back into the affine coordinates. So, for that actually, I mean, I am not going into this, but you need to do one inversion at that point is necessary. Okay. So, this is actually straightforward, because this is exactly like the previous algorithm. You have basically this step, right. So, see, for example, you had y1 as x1 plus x into, so you basically what you did there was, if you see the y1 equation, was x 1 plus x into x 1 plus x into x 2 plus x square plus y. This was divided by x plus y, that was your y coordinates, right. So, now your transformation in your projective coordinate system is x is equal to x by z, your y is y by z square. Okay. So, if you do this, then what you will write here is you will take this point. So, therefore, you see that if you want to do this conversion, okay, you will write here this x as x, this x 1 point you will write as x 1 by z 1, okay, and your x 1 plus x again you will write as x 1 by z 1 plus x, x 2 you will write as x 2 by z 2 plus x, right, plus x square plus y, right, and that is divided by x, and again point y is added, I mean y is added, right. So, therefore, this you can actually simplify and you can write as x plus x 1 by z 1 and this as x 1 plus x into z 1, x 2 plus x into z 2. So, you see that there is a z 1 by z 2 at the bottom, then you have got x square plus y, and you can actually write all these z 1 z 2, okay, z 1 z 2 and minus inverse, right. So, therefore, x into z 1 z 2, okay, plus this term y, right. So, therefore, you see that all these terms x 1 and your x 2 and your x 1 and your x 2 and your z 1 z 2 are there in the projective coordinates. You are using these projective coordinates and you are basically applying only one inversion operation to finally convert your projective result back into the affine coordinates, right. And the corresponding x thing is very simple, because you just need to divide this by the corresponding z to obtain the x coordinate, right. So, therefore, the if you want to obtain x 3, that is the result of p 1 and p 1 plus p 2, the x coordinate, you just need to divide x 1 projective coordinate x 1 by z 1, and for the y coordinate you need to do more operations. Actually, you need to do 10 multiplications and one inversion operation to do the final transformation. So, if you do a neck to neck comparison of the affine coordinates and projective coordinates, this is how it looks like. There is a more, the inversions are reduced, but the multiplications and the additions and the squarings have of course increased, right. So, therefore, whether you will go for your affine coordinates or whether you will go for projective coordinates depends upon your I is to m ratio, that is in your inverse how many multiplications or multipliers are there. Okay. So, that actually dictates whether this one is more efficient or whether this one is more efficient, right. So, there are, I mean, I will not go into this, that is there are some approaches which says that you actually keep one of the points in projective coordinates and keep the other point in affine coordinates. So, that is called as mixed coordinate systems. So, these are some equations which are derived, which you can check also offline, that is, but in this case the main thing to be pointed out here is that the number of multiplications are further reduced, squaring is increased a bit, but they are cheap in GF 2 power of n. There is a 10% improvement if a is not equal to 0, and if so a is 0, then there is a 12% improvement. So, mixed coordinate systems are at times more efficient than even the projective coordinate systems. So, I will just finally conclude with some comments on parallelizing strategies on the point doubling and the point addition operation. Okay. So, you see that in your point doubling, so I am considering the projective coordinates here. So, these are the operations that you did. Okay. So, therefore, you just think of x 1 comma y 1, what you have done here is this, that is you have taken this x 1 squared it, c z 1 square, z 2 is t into z 1 square, and finally, you are adding this t square plus m square, and this is your double point. Okay. This you can check, okay, that is this is exactly the same as what we did previously. So, how many multiplications are necessary here? There is one multiplication operation necessary. Multiplication with constant I am not again considering as multiplication. So, if I have got one multiplier, then that is sufficient to do this operation. But what about doubling? You see that there are more number of steps. Okay. So, here for example, there is one multiplication, here is another multiplication. So, if I want to do a parallelization, then I have to, and there is again a multiplication here, again a multiplication here. So, if I have got two multipliers, then I can actually parallelize this step and I can parallelize these two steps also, right. So, therefore, depending upon my resource constraint, I can actually parallelize this point addition also. Okay. And what will be the final, I mean, so if we just see of this Montgomery's algorithm structure, if I want to parallelize this, I can parallelize this probably at various levels, like I can either parallelize this at this level of Kp, or I can parallelize the inherent internal doubling and addition operations. Okay. That is, I can either parallelize level 1 or I can parallelize level 2. Okay. So, here are some comments, like suppose if we allocate one multiplier to each of m add and m double, one multiplier to each of m add and m double, then we can parallelize steps 5a and 5b. Okay. So, we have got two multipliers, we are allocating one to the addition and one to the doubling, right. So, you see that here you are actually doing the addition and then you are doing the doubling in parallel, because you have two multipliers, you have actually given one multiplier to this and one multiplier to this, and you can actually doing both of them in concurrence, right. So, what will be the cycle length required? Will be that equal to that required for the addition, because addition is more, right. And you know that from these steps, if you have got one multiplier instead of two multipliers, then for this you need 2 time steps, because first you have to do this, then you have to do this, or you have to do this and then you have to do this. You can't do these two things in parallel, right. Similarly, here you can do either this or you can do this, you cannot do them in parallel. So, how many clock cycles? You need to do 1, 2, 3 and 4. So, you need to do 4 clock cycles for doing this, and therefore, for every time step you need to do 4 L. So, therefore, if L is the number of times you are iterating this loop, you require 4 L number of clock cycles, nearly 4 L. But suppose that if you have got, like if you can parallelize the underlying m add and m double, then you cannot parallelize the level 1, because you have got again a constant of 2 multipliers. So, therefore, if you can parallelize the underlying m add and m double, that means you have actually given 2 multipliers to this, right, because that is the way how you can parallelize this. Then you cannot do the addition and doubling simultaneously, because you have got a constant of 2 multipliers, right, because you do not have 3 multipliers, right. If you had 3 multipliers, you could have done parallelize this as well as perform the doubling and addition in parallel, right. So, now since you have, if you have parallelized this, you have to do this and this in sequence, which means for this you need 2 clock cycles, because you have parallelized this and you have parallelized this. So, basically you can do this addition in 2 clock cycles, but the doubling also will need 1 clock cycle, and since this doubling and addition has to be done in sequence, you need 3 clock cycles to doing this, and this you will iterate and you will require 3L number of times for doing the entire operation. And suppose you have got 3 multipliers, that is, you have got more resource sorry, then you can actually do this operation in lesser time. You can do that in 12 clock cycles sorry, right. So, that means you see that Montgomery's algorithm is highly parallelizable depending upon your constraints and your requirements of power and throughput. You can actually, there is a spelling mistake here, is throughput. So, therefore, you can actually make high performance designs for doing the scalar multiplications, right. So, there are a lot of things to concentrate and think of over here. So, one of the things is like there is something is called Kobli's curve standardized by NIST out of the form as y square plus xy equal to x cube plus ax square plus 1 over a binary field. You can take this exercise to compute the number of additions and doubling equations for points on these curves, and again compute the number of multiplications and inversions to be performed in affine, projective and mixed coordinates what we have seen. Okay. So, you can rework this on specifically these kind of curves where this constant a is equal to 1. So, here some of the references, some of the classic papers that are followed are this Lopez and the Hub, which is published in Chess 1999, and also some of the other important references are mentioned here, and the books are standard this. So, next day we will take up the topic of secret sharing schemes.